This is the second lecture in the chapter 13 look at solutions and their properties. Today we're going to talk about some of the ways that a solute can alter the inherent properties of a solution, and we're going to talk specifically about a group of properties called colligative properties. So these are changes or characteristics of a solution that are dependent upon the amount of the solute, but not the type of the solute. We've talked in the last chapter about how the type of solute and solvent can have an impact on the behavior of the solution. And in this case, we're going to be looking at the concentration of the solute and how its value can affect the way that a solution behaves. So the properties that we're going to talk about are vapor pressure, freezing and boiling point, and osmotic pressure. Vapor pressure is a colligative property that looks at the balance between molecules in two different states of matter, in both the liquid phase and the gas phase. So if we shift this out of the way for a moment, and we imagine that we have this solution, the solution includes particles in the liquid phase. Whoops, there we go. In the liquid phase. And if this solution is subjected to heat, for example, then we will get some collision of particles within the liquid running into each other, into the sides of the container and whatnot. And as these particles come into contact with the air above the level of the solution, some of the molecules of whatever this liquid is will escape into the gas phase. They'll form a vapor. So the vapor pressure looks at the equilibrium between the pressure of the molecules above this solution, the pressure of the molecules that are in the gas phase, compared to the pressure of the molecules within the solution that are still in the liquid phase. So that's the idea behind vapor pressure. It's important to talk about, though, what kinds of substances are really being described in this example of solutions. Volatile substances are very likely to form gases when heated. So volatile substances are things like water, for example. When you heat water, it quite easily becomes gaseous water. Non-volatile substances are those which are not likely or have very little tendency to become a gas. So when we talk about the colligative properties in solutions as relate to vapor pressure, we're primarily dealing with non-volatile substances as our solutes. So we're adding things like salt, for example, or sugar. Those are substances that do not themselves become gases very easily. And what happens to vapor pressure when you add a non-volatile solute to a solution, to a liquid, it causes there to be decreased collisions between the solvent molecules themselves, because now there are solute particles dissolved and kind of getting in the way of solvent-solvent interactions, and therefore fewer molecules of solvent are able to escape from liquid to the gas phase. So what happens is the vapor pressure, the overall pressure of the solution compared to the gas phase, it decreases. And the thing that's really interesting, and because this is an example of how colligative properties are based on concentration and not on type of solute, equal concentrations of any two solutions will have an equal vapor pressure depression or vapor point depression. So that's pretty curious. The next colligative property is freezing point. And freezing point is a property, you'll remember, it's inherent to all substances. All substances have a point at which they go from liquid to solid. There's a set temperature. The freezing point of any solution with a 1 molar concentration, so salt water or sugar water or I don't know, any other solute you can think of off the top of your head. A 1 molal solution has nearly a 2 degree lower freezing point than pure water would. So just the addition of salt or sugar will lower the freezing point of pure water nearly 2 degrees Celsius. The thing that's interesting about this is we can use that knowledge to make predictions about certain products or how a reaction might proceed under certain conditions. And it also allows us to work with another constant, so similar to molar mass, right? Molar mass being grams per mole. We've got a constant here that looks at the molal freezing point. And that constant is a capital K with a subscript F. So that's the freezing point constant, and it is equal to this value that I mentioned above, negative 1.86 degrees Celsius per molal of solution. This value is inherent to the solvent being used. So in this case, we're dealing with water. This is the freezing point constant for water. And there are changes in the constants depending on the environmental conditions, but at standard atmospheric pressure, so in regular lab settings, the solvent has a fixed freezing point depression. We can compare solutions of pure solvent and solutions, with a 1 molal concentration by using a value called freezing point depression. And this value is measured in degrees C, and you can see it right here. It's delta. Delta in scientific purposes, we use delta to represent any change. So delta Kf represents the change in freezing points between pure solvent and a solution that includes the same solvent. We'll do some calculation practice with that in class. The third colligative property is boiling point. And so we've talked a little bit about this in class when we did the ice cream activity, but as you might expect, as the vapor pressure changes, or how easily a liquid becomes a gas, we have a similar change in boiling point, because boiling point is in fact the transition from liquid to gas. So we have a constant here as well. It's called the molal boiling point constant. And this describes the amount of temperature change per molal solution of any given solvent. So the value for boiling point is K with a subscript of B for boiling point constant. You can see that this value is quite a bit less than the freezing point depression for water. The boiling point elevation is only about 0.5 degree Celsius per 1 molal concentration solution. So that's a quarter as much of a change as we saw in freezing point. But just like freezing point, different solvents have different values. And again, if we're dealing with standard temperature and pressure, regular lab conditions, STP means standard temperature and pressure, these values are fixed. And again, we can look at the change in boiling point. And so we have another change, delta KB, that shows us the change in boiling point between pure solvent and solution-based solvents. Our last colligative property is osmotic pressure, and we're not going to spend a bunch of time on this. You talked about osmosis in depth, I believe, in biology last year. So remember that osmosis is the movement of water through a semi-permeable membrane. So we've got this membrane, for example, that's separating two different solutions. So we'll say this solution is pure water, no solvent of any kind, or no solute, pardon me. And then on this side of the semi-permeable membrane, maybe we've got sugar water. And so there's sugar and then there's water. Let's make this. There we go. And then the blue would just be the water, like on the other side. So remember that osmosis is the movement of water through a semi-permeable membrane in an attempt to create balance. So in this case, in all cases of osmosis, there's more water on the left than there is relatively on the right. And so water will feel an osmotic pressure, pardon me, in order to stop the movement of water from the left side to the right side. There would be external pressure would have to be exerted in order to keep this process from happening. This is a natural equilibrium-based process where we want to have equal concentrations of water on both sides. The more solute you add to a solution, so let's say we dumped in additional sugar over here on the right, the osmotic pressure is going to increase even more. You would have to do significantly more work externally in order to prevent water from moving into this solution. And osmotic pressure is incredibly important in the functioning of the human body as well as many other animals, primarily in the kidneys. Osmotic pressure is what keeps your body balanced in terms of water and salts and keeps you from dehydrating, among a few other things. So the discussion of salt and water again leads us back to electrolytes. So remember that substances or solutes that tend to break apart into ions, that tend to dissociate, are called electrolytes. Those that do not are non-electrolytes. So colligative properties are based upon the amount of dissolving and the amount of ionic dissociation that exists. So we're going to deal just with electrolytes at this point. And the amount of, say, freezing point or boiling point change that you see in a solution is due to the overall concentration of ions. So let's say MgCl2 versus AlCl3. This will have 3 total ions in solution, 3 total moles, whereas AlCl3 will have 4 total moles in solution, right? It'll dissociate into 4 moles total. The greater the concentration of ions, the larger the change in colligative properties. There are fixed values. Certain ions will, in fact, have certain degrees of change in each colligative property, and we can predict those values. We have tables that show predicted values. The actual solutions may not have that exact change because there is some degree of I guess individuality within solutions and the amount of interference that ions will cause at any given time for the solvent molecules. But generally speaking, the predicted values are very close to the actual values. The more highly charged ions, the say Al3 plus, for example, will cause greater interference in a solution than would a single potassium ion. And we'll talk again more about this in class. We'll do some examples with these calculations. I think it's easier to do in person. So please write some clarification questions and your summary, and I will see you in class.